Hi everybody, it is Miss Weeson, and we are at the top of page 6, getting ready to watch our third podcast of Unit 5, Chemical Kinetics. Today we're going to learn about rate expressions, or more specifically, the differential rate law. And this is going to be a rate law that we write, and it's going to express how the rate of a chemical reaction is going to depend on a change in concentration. Now, most of you can probably agree that right at the onset of a chemical reaction, we're starting with 100% of our reactants and 0% of our products. And if we were to hit the go button on a chemical reaction, if you will, we would see that right at the very beginning, the initial rate of reaction is probably going to be pretty high. And as the reaction proceeds, that rate of reaction might decrease until the rate gets to zero, right? Until we have 100% product formation. Now, I just want to plant this seed in your head, but most of you at this point have learned that, generally speaking, when you start off with reactants, we draw an arrow to indicate chemistry is happening to form our products. Now, what if I told you that most reactions are indeed what we call reversible, meaning that once we have product formation, they can actually revert back to reactants. And so in this particular case, it would be appropriate to draw a double arrow. Now, we then would say that the rate of the forward reaction would be then equal to the rate of the reverse reaction. Now, this is something called equilibrium, and we're going to get to this later. I believe that's our 7th unit of AP Chemistry. I just bring this up to kind of plant the seed and keep it in the back of your mind that chemical reactions are indeed reversible. And when we do the differential rate law, we need to kind of know that. But what we're going to do is we're going to look at the differential rate law from the perspective of right at the onset of a chemical reaction. In other words, we're going to deal with initial reaction rates. In other words, we're going to look at the concentration of our reactants right at the onset of the chemical reaction, right at the beginning. So oftentimes we call this the method of initial reaction rates. And we're going to assume, again, when we take this approach, that we're beginning with pure reactants before we mix them together and before we allow the chemical reaction to occur. And once we do that, we can actually then measure the production of the products over a span of time. Now, we can, of course, measure chemical reactions, and we can witness them happening by counting the number of bubbles forming, if that's the case. Some chemical reactions have a precipitate that falls out, and later on we could mask that precipitate, or we can even analyze the color change of a chemical reaction using a lab technique in spectroscopy. So what is the differential rate law? Let's look at an example really quick in our notes. And it says to consider the chemical reaction and to write the differential rate law of this reaction right here. Now, prior to this podcast, you guys had learned, and you shall never ever forget, that a rate is equal to some change in some measurable quantity over a unit of time. So, for example, if we're using the reaction, we could say the change in concentration of the reactant divided by a unit of time. Don't forget, you guys, we'd actually get a negative number here because, remember, as products are decreasing, you would get a negative value. And so, although this rate law is true, we are now going to express the rate in a different way. The differential rate law, we are now going to express rate using a mathematical equation. So take a look. The differential rate law for the reaction would look like this, and I just circled it. And in just a second, we're going to break this down and learn how to set up these rate expressions. Okay, so how is it that we actually set up this differential rate law? Down at the bottom part of page 6, I am going to kind of teach you how to set up these rate expressions, or the differential rate law, if you will. And you can see that I gave you a generic reaction. And right below it, I listed how you would indeed write the rate expression from the balanced chemical reaction. And then even below that, I listed what all these variables mean and how to define them. So when you write the rate expression, you're going to notice now we have a lowercase k here. And you'll see that k is nowhere in the reaction. And that is because the rate expression now involves a constant. And so lowercase k is indeed going to be something we call the rate constant. Now, continuing on with the rate expression, you will see that each reactant, which in this case is A and B, we are going to, in the rate expression, need to know the concentration of the reactants, and that's why you see brackets. All right, brackets mean molarity, which is moles per liter. And then you're looking at what C is. What is C? Well, if you go back to the chemical reaction, this generic reaction that I wrote, C is placed above the reaction arrow. And if you go to the kind of list here of what these variables mean, the C in this particular case is representing a catalyst. Now, not all reactions are going to involve a catalyst, so you might not involve this in a rate expression if you don't have a catalyst involved. But if you do, you absolutely need to include it as a part of your rate expression. So again, why are we placing the catalyst above the arrow? Well, we learned earlier that a catalyst is not used up in a reaction and is simply there to lower the activation energy of the reaction for allowing it to proceed forward. So in this case, it would be appropriate to write it above the arrow. And so again, you need to know the concentration of your catalyst, and you would include that in your rate expression as well. So one thing you should notice is when you write rate expressions, they do not involve products. They only involve the concentration of the reactants. One more thing about this rate expression you should notice is that each one of the reactants and the catalyst in this case is raised to a certain order, is what we call it. And so if you come down here to the key, M is the order of reaction for reactant A. The letter N is the order of reaction for reactant B. And P is the order of reaction for the catalyst. Again, we're going to call those exponents orders, and we're getting ready to learn about what they are. And make a note here that the order can indeed be zero. They could be whole numbers or they can be fractions. Either way, they're going to be determined through experimentation. So in this particular next set of material we're going to cover, you are going to set up the rate expressions using a series of concentration and rate data. Okay, so before we jump into a practice problem, I do need to front load some more information on you. Let's talk a little bit more about that rate constant. Again, it's lowercase. Now, the rate constant, depending on the order of the reaction, and we'll talk more about that here in a second as well, but depending on the order of the reaction, K is indeed going to have different units. The rate constant is also temperature dependent. And again, it must be determined and evaluated by experiment. Now, in a little while, I will derive and show you all of these units and what the units would be for K depending on the order of the reaction. Now, let me give you a little bit more on orders, the scoop on orders. Now, when we say the word order, we're talking about with respect to a certain reactant, okay? And this is simply the exponent, and it's occurring right outside the concentration brackets for that particular reactant in the rate expression. Now, one more time, we must analyze concentration and rate data to know and make the determination of what the order is of a particular reactant. Another term you're going to hear that you would possibly see is determining the overall order of a reaction. Now, when we say that, this is simply the sum of all the exponents of the concentration terms in the rate expression. Okay, again, we will do some examples. Patience, it's coming. There are generally three different orders that you need to know in AP chemistry. A reaction, or rather a reactant, can be zero order, first order, or second order. And I'm just going to forsake zero order. You would literally write a zero. For first order, you would write a 1, and of course, a second order, you would write a 2. Now, if a reactant is zero order, That means when you change the concentration of that particular reactant, it is not going to have an effect on the rate of that particular reaction. Now, these aren't very common, and so when you have a reactant that is zero order, the general form of that would be rate equals K. And here's why. Because if you actually have a reactant, let's just say reactant A, you guys. Let's just say you have a reactant, and we have determined that when we increase that concentration of A, it's not having an effect on the rate. Therefore, we would put a 0 there, right? Well, anything that's raised to the 0 power is going to be equal to 1. You could simply say K is 1, and therefore rate is equal to K. Okay, what if a reactant is first order? Now, these are going to be probably the most common. So what does a first order reactant mean? That means that the rate is going to be directly proportional to the reactant's concentration. In other words, that if you double a reactant, the rate doubles. Okay? If you triple a reactant, the rate's going to triple. If you quadruple a reactant, the rate is going to quadruple. So the general form that you would write if a reactant was first order, and you can see it here in your notes, is you would say rate equals K. You would put in brackets the concentration of A, and you would raise it to the first power. Now, as an example, and you guys probably know this from math class, if you said rate equals K, and let's just say we actually had a value of concentration, I don't know, 2 as an example, and if that reactant is a first order reactant, then of course, what you'll see here is that the rate doubles if we actually double the concentration. Then, so what is a second order reactant? So when you have a reactant that is considered second order, basically doubling the concentration of that reactant will quadruple the reaction rate. Or tripling the concentration of that reactant will increase the rate by 9 times, right? These are very common. Second order reactants are very common when the reactions are largely gas phase reactions. And you can see that the form that they take here, you would just simply put a 2 exponent outside the reactant that is indeed second order. Now, what you're noticing here is I gave you 2 possible options. The rate could be second order if there's only 1 reactant, or look at what else. You can have an overall order of 2 if you have a reaction involving 2 reactants and each of them has the order of 1, at which point if you were to take the sum of both reactants, you would have an overall order of 2. Make a note, fractional orders are rare, but they do exist. I do not think they are in the scope of the AP chemistry curriculum, so we're going to focus on 0 order, first order, and second order reactions only. And I want you to be very clear. It's important that when you write about this and you're doing your work, especially with College Board, that you're using the correct language. And so what I have done here in your notes is I gave you a generic rate expression, and I want you to take a second and pause me and look at how you would actually speak in terminology when a particular reactant is of a particular order. For example, if reactant A is 0 order, you would say the reaction is 0 order with respect to A. Now, I'm not going to read all of these to you, but generally speaking, this would be the appropriate way to write and talk when speaking about rate expressions and orders. I think we are ready to try an example. So page 8 is basically just a generic example. And the reason why I say that is because we're just going to use a generic reaction. A plus B yields our products. So in this particular reaction, we're going to write the differential rate law, or the rate expression for this particular generic reaction. Again, I keep saying this, but you are going to need a data set of a rate data and concentration data. And so put me on pause and take a look. Here's our data. I have ran 5 different experiments. I went ahead and pulled out the initial rate out of scientific notation. For some of you, it might be easier to see how rates are changing when they're, not in scientific notation. You don't have to do that though. I'm also given initial concentrations for either reactant. So it looks like we ran an experiment 5 times where we just varied the concentrations of either reactant to see how the rate would be affected. And so another thing, I literally listed out step by step what I was thinking and the process here. I'm not going to read this to you, but what I want you to do is that after you are done seeing me go through this particular example and how we arrive at the rate expression, I then want you to go back and reinforce that new learning by reading these steps that I've included for you. And hopefully that'll kind of give you more of an overview. Now, generally speaking, where I start is that I am going to look at a reactant where it is held constant. Okay, so you're going to take your eye, analytically look at your data, and look for two trials where the concentration of one of the reactants was held constant. And so I'm just going to arbitrarily look at, let's go to reactant A, and I see that in trial 1 or experiment 1 and experiment 4, that the concentration of A was held constant. Now, what you are then going to do is you are going to look at how holding A constant, what happened to B. So it looked like when A was held constant, the concentration that is, that B doubled, right? Because 0.2 and 0.4, that's a doubling of the of concentration B. Now, when reactant A was held constant, it looked like B was doubled. Now, the last thing that you need to do is then go and look at rate. So what happened to the rate? Well, when we doubled B, it went from 0.005 molarity over seconds, or in this case, over hours, to trial 4, when it was doubled, it went to 0.01 molarity over hours. So wouldn't you agree that when we held concentration A constant and B doubled, the rate doubled? Okay. If we went back and talked about what a zero order reaction was, a first order reaction, and a second order reaction, what order does that sound like? So I'll say it again. When we had the concentration of B double from 0.2 to 0.4, what did you notice about the rate? The rate also doubled. So in this particular case, it looks like B is first order. So to start writing that rate expression, you would say rate equals, don't forget you're always going to have a rate constant, and we'll come back to that. We're trying to figure out the order for A. We haven't done that yet, but we just determined that the order for B was a first order. Okay, and if you don't believe me, what you can do then is you can say, well, from trial 4, we're comparing trial 1 and 4. The rate of B doubled, right? And when that happened, it looks like our rate also doubled. And that's directly proportional. That is the definition of a first order reaction. Okay, now we need to determine the order of reactant A. Again, you can only do this with a data set, which is why we're breaking this down on a data table. So I'm going to go ahead and erase all of this stuff right here so it doesn't get in our way. And now what we're going to do is look at two trials, and we're going to hold the concentration of B constant, and we're going to look at what happens to A's concentration as well as the rate. So pick two trials in for B where it is held constant. Now, I know you're going to see that there's multiple places where B is held constant, but I'm going to look at trials number 1 and 3. Can you take a guess why I would choose 1 and 3? Well, look, when you hold B constant, initially in experiment 1, the concentration of A was 0.5. And when I went to experiment 3, I noticed that it doubled to 1. I like looking for doubling. It's my personal favorite. It doesn't mean it's always going to happen. It depends on the reaction. But doubling is my personal favorite because even on my worst day, I can multiply by 2 and divide by 2 and square 2 and even cube 2 all without a calculator. So what I'm trying to say here is I'm looking at data that is easy for my brain to interpret. So again, we held B constant this time. Now we're looking at A's concentration. A's concentration is doubling from 0.5 to 1. And now you then have to say, okay, what happened to the rate in that time? Well, let's take a look. The rate initially was 0.005 molarity over hours. And at trial 3, oh my gosh, the rate stayed the same. So it didn't matter. We doubled A, but the rate stayed the same. I'm going to say that one more time. We doubled the concentration of A, yet the rate stayed the same. Go back to your notes and tell me, what order of reaction is that defined as? If you said zero order, then you're spot on. So go back to your rate expression and you will write a zero up here as your exponent or order for A. If you don't believe me, let's take a look. So again, in this case, we're comparing trials 1 and 3. If we took the initial concentrations, we can see that they doubled. Yet if we go and look at the rates during those same trials, we could see that it stayed the same. Thus, doubling the rate did not increase. Thus, doubling the concentration did not do anything to the rate. Okay, I know that was really quick, and you can see here that I put into quite more detail and wording. So I encourage you, please go back and reread these steps 1 through 4 at the bottom of page 8. Okay, let's give it another try. At the top of page 10, let's do exercise 2. And you can tell here with the reaction that is given, they're telling us that the cobalt chloride bond in the reactants is going to be replaced by the cobalt hydroxide bond in the products. It gives us a reaction. And notice it also actually gives us the rate expression. Now, rate expressions really quick only involve the reactant, so you can see that here. We also are not quite sure what the order of that reactant is. Therefore, we are given down below concentration and rate data, and now we're going to figure out the order of this reactant. And so I made a mistake here. If you guys want to make a quick adjustment on your notes, I copied experiment or trial 4. It's just a repeat of the first trial, so we don't actually really need this last experiment here. I'm not sure why I did that, so I'm sorry. Okay, so what we're looking at is your initial concentration between 3 different trials here. Now, if you look at the initial concentration between experiment 1 and experiment 2, okay, I'm kind of bracketing it right here. What do you notice? You notice that the concentration is doubling here. Now, since we're only dealing with one reactant in this reaction, go ahead and take a look at how the rate changes, okay? So how does the rate change? Well, if you double the rate, which it looks like the rate is doubled, and the concentration was doubled, then it looks like this is going to be the definition of a first order reaction. As you increase in concentration or double in concentration, you are going to double the rate. So that sounds directly proportional, and it definitely sounds like a first order reaction. Now, you can also confirm this again if you take a look at and compare the concentrations between trial 1 and trial 3. If you triple that concentration, then go ahead and now take a look at the rate. I'm going to bracket it over here. Well, it looks like you triple the rate. Again, when you triple the concentration and the rate triples, that looks like it is directly proportional and is therefore a first order reaction. Okay. Now, then you would go ahead and now you know what the value of M is in the rate expression. So let's go ahead and rewrite it. So now that you've determined the order of the rate expression here, or the order of the reactant from the concentration, if you will, you can actually solve for K, right? Because if you look at the data table above, the data table is giving you rate data. It is also giving you concentration data of the reactant. And so what you can do is simply rearrange this equation to solve for the rate constant. And this is a common question that you'll be asked often. So if you rearrange this equation, ultimately what you would get is K equals rate over the concentration of the reactant to the first order. And now we could simply just pick any trial that you want. I usually just go with the first trial listed to determine what the rate constant is. And so K equals, again, we're just going to use the first trial data here to plug into our rearranged rate expression. And so in our numerator, my rate would go up in the numerator. So it's 1.3 times 10 to the minus 7. Now make a note. Let's go up here and look at the units, you guys. Okay, again, if you look at moles per liter, that's molarity over minutes. All right, so that's basically your unit for rate up here, and you can see that is basically given to you in the data table. And then you would divide that by the concentration in the same trial, which is 1.0 times 10 to the minus 7. And of course, concentration is in molarity, moles per liter, as it says. Go ahead and cross cancel like units and rewrite, do your calculation. And when I plug this in onto my calculator, I got 1.3 times 10 to the minus 4. And make sure you port your units over. Don't forget your units. We just, in the previous page or so, we went and derived all the units from the first, second, third order reactions. And this unit should look pretty familiar to you. Okay, you guys. Well, that is basically how to use concentration rate data to arrive at the rate expression and also to be able to determine the order of the reactants that are listed in the rate expression. I think number 3, exercise 3, is something that we could do together as a class. You can see here that this is a little bit more involved. We're dealing with a reaction that has 3 reactants. And so our data table of concentration and rate data is going to be a little bit more involved to break down and determine the orders of each of these reactants. So let's go ahead and do exercise 3 in class together. And that's going to be it for now on the differential rate expression. Thank you so much for watching. Bye-bye.